The plains cut different in southeastern Wyoming territory. Jakob Klaus learned that his second winter in 1876, when frost formed between his floorboards and his wooden floor, stayed cold as stone 3 feet from the stove. He had built his floor exactly the way every homesteader in the territory was told to: wooden planks over raised joists, square nails, standard and trusted. By spring, settlers across the Wyoming plains were fighting the same losing battle with floors built by the book and failing by the season. His neighbors mocked him when he quietly switched to what they called just a dirt floor, backward and primitive. But when the brutal winter of 1887 hit, Jakob's packed earth floor stayed warmer, used less wood, and outlasted every wooden floor around him. We'll break down the exact steps and principles behind this forgotten frontier technique. What did this German stonemason understand about thermal mass that every other settler missed? Jakob Klaus had followed the rules exactly when he first claimed his 160 acres in the spring of 1875. The Territorial Land Office guide was clear. Proper homestead improvements meant wooden floors, raised foundations, and frame construction that demonstrated civilization over wilderness. He had the skills to do it right. 20 years working stone in the Bohemian provinces had taught him to read ground conditions. But here in southeastern Wyoming territory, surrounded by rolling sagebrush plains and the distant peaks of the Laramie Range, he trusted local wisdom over old country methods. His first cabin followed the pattern every settler in the region used: wide plank pine boards, 12 inches across and 2 inches thick, laid over hewn log sills that raised the floor 18 inches off the ground. Square-cut iron nails driven every 16 inches held the planks tight. The crawl space underneath stayed open to allow air circulation, just as the territorial building guides recommended. It looked proper, felt solid underfoot, and satisfied the district inspector who noted adequate floor improvement on Jakob's claim documentation. But by October of his first year, problems began surfacing that no one had warned him about. The wooden planks developed gaps as the dry Wyoming air shrank the pine. Cold air flowed up between the boards, creating drafts that chilled his ankles, even when the wood stove glowed red. Worse, moisture from the ground began condensing on the undersides of the floorboards. By November, he could see frost forming in white patches beneath the planks when he crawled under the cabin to check his foundation posts. His neighbor Andrew Merrill, working the claim 300 yards east, faced the same issues but dismissed them as normal frontier hardships. Merrill had arrived from Pennsylvania 2 seasons earlier and insisted that wooden floors, despite their problems, marked the difference between civilized homesteading and primitive camping. When Jacob mentioned the cold drafts and underfloor frost, Merrill shrugged and said every cabin dealt with such minor inconveniences. The important thing was having a proper floor that could be swept, mopped, and nailed down tight. But Jakob's experience in the Hungarian plains had taught him different lessons about ground contact and thermal behavior. In the old country, he had worked on rural buildings where peasant families used tamped earth floors that stayed comfortable through harsh continental winters. An elderly mason named Tomasz had explained how dense earth absorbed heat from cooking fires and radiated it back through the night, creating steady warmth that wooden floors could never match. The old man had called it making the ground your friend instead of your enemy. That knowledge seemed irrelevant in Wyoming territory until Jakob began measuring the actual temperatures in his cabin. Using a simple thermometer, he tracked floor surface temperatures through his first winter. On a typical January morning, with outside air at 20 degrees above zero, his wooden floor measured 34 degrees at dawn. The planks felt like ice blocks under his bare feet. Meanwhile, he noticed that patches of bare earth visible through gaps in his floorboards stayed noticeably warmer, holding temperatures around 42 degrees even on the coldest mornings. The contrast puzzled him until he remembered Tomasz explaining thermal mass behavior. Wood was a poor heat conductor and a worse heat storage material. The pine planks changed temperature rapidly, cooling fast when the stove died down, and warming only slowly when the fire blazed. But earth, especially dense clay-rich soil, absorbed heat energy and released it gradually. The ground beneath his cabin, insulated by 3 feet of prairie sod and protected from wind, maintained more stable temperatures than the exposed wooden surface above. When Jacob mentioned these observations to his neighbors, the response was swift and dismissive. Merrill laughed openly, calling Jacob's measurements immigrant nonsense and insisting that any fool could see wood floors were warmer than dirt. The district inspector, making his annual improvement assessment, noted that Jacob's floor met territorial standards, but warned that experimenting with primitive methods could affect his claim valuation. Several other homesteaders began referring to Jacob's temperature measurements as evidence that the German doesn't understand American building. The mockery intensified when Jacob began discussing alternatives. At a community barn raising in late winter, he suggested that tamped earth floors might perform better in the local climate. The response was immediate ridicule. Merrill declared that only Indians and Mexicans used dirt floors, while proper American settlers built with lumber. Another neighbor, Hans Müller, who had immigrated from Bavaria, surprised Jacob by joining. The criticism, insisting that wooden floors represented progress and that reverting to earth floors would be moving backward toward the Dark Ages. But Jacob had seen enough evidence to trust his measurements over popular opinion. The combination of his European craft knowledge and direct temperature observations convinced him that conventional wisdom was wrong for Wyoming conditions. Dense earth in direct ground contact could outperform raised wooden planks in thermal comfort and fuel efficiency. The question was whether he had the courage to abandon accepted methods and risk his standing in the community. By spring of 1876, Jacob had decided to test the principle on a small scale. He removed the wooden planks from a 6-foot by 8-foot section of his cabin floor, exposing the bare earth beneath. He then excavated 6 inches of loose topsoil and replaced it with a carefully prepared mixture of local clay and coarse sand in roughly equal proportions. Using techniques learned from Tomasz, he tamped the mixture in thin layers until it formed a dense, level surface 2 inches thick. Finally, he sealed the packed earth with 2 coats of boiled linseed oil, creating a smooth, dirt-resistant finish that gleamed like polished stone. The result established the central conflict that would define Jacob's homesteading success. On one side stood accepted territorial wisdom. Wooden floors represented civilization, progress, and proper American building methods. On the other side lay an older principle drawn from European peasant craft. Dense earthen mass could store and radiate heat more effectively than lightweight wooden materials. Jacob's small test section would either vindicate traditional knowledge or confirm his neighbor's assessment that he was a backward immigrant clinging to primitive methods. The success of Jacob's test section through the winter of 1876 convinced him to expand the technique, but the full floor conversion required solving problems that the small sample had not revealed. The 6-foot by 8-foot packed earth area had performed exactly as he hoped, maintaining surface temperatures 5 to 8 degrees warmer than the surrounding wooden planks. But scaling up to his entire 16-foot by 24-foot cabin floor exposed complications that threatened to undermine the whole project. The primary challenge was ground preparation on a larger scale. Unlike his test patch, which had been excavated by hand in a single afternoon, preparing the full subgrade required systematic soil analysis and careful attention to drainage patterns. Jacob discovered that his cabin site contained 3 distinct soil layers: 6 inches of loose prairie topsoil, followed by 18 inches of dense clay mixed with gravel, then a deeper layer of coarse sand and rock fragments. The topsoil was too loose to support a stable packed earth surface, while the deep clay layer retained moisture that could freeze and heave in winter. Working through late spring of 1877, Jacob developed a subgrade preparation method that addressed these soil conditions. He excavated the entire floor area to a depth of 6 inches, removing all loose topsoil and exposing the clay-gravel layer beneath. But instead of building directly on this clay, he created a drainage base using materials found on his claim. He hauled 2 wagon loads of coarse sand from a dry creek bed half a mile south of his cabin, spreading it in a 1-inch layer across the excavated area. Over this sand base, he placed a second layer of crushed limestone chips, gathered from a natural outcrop near the Laramie foothills. This 2-layer drainage system solved the moisture problem that had plagued several neighboring cabins. The sand layer allowed groundwater to move laterally away from the floor area, while the limestone chips provided a stable base that would not shift or settle under the weight of the packed earth surface. Jakob learned this technique from an unexpected source during his excavation work. A Shoshone elder known locally as Chief Green Rock had been observing Jakob's construction from a distance, curious about the white settlers' unusual building methods. When Jakob struggled with water pooling in his excavation after a spring rainstorm, Green Rock approached and examined the work. Speaking a mixture of English and hand signs, the elder explained how his people prepared earth floors for winter lodges. The key principle, as Green Rock demonstrated by scooping up handfuls of different soil types, was creating layers that drink water down, not up. Dense earth for warmth belonged on top, while loose gravel and sand belonged underneath to carry moisture away. Green Rock's most important lesson concerned the relationship between earth floors and the deeper ground. Unlike raised wooden floors that isolated living space from soil temperatures, packed earth floors worked by connecting to the thermal mass of the ground itself. The elder pressed his palm against the excavated clay layer and explained through gestures that winter ground stayed warmer than winter air. "Earth holds yesterday's heat in its skin," he said, using one of his few English phrases. A floor in direct contact with stable subsoil could draw on that stored thermal energy throughout the cold season. This insight led Jakob to abandon the crawl space concept entirely. Instead of raising his floor above ground level, he would build it flush with the surrounding terrain, creating full contact between his living space and the Earth's thermal mass. But this decision created a new technical challenge, preventing cold air infiltration around the floor perimeter where the packed earth met his log walls. The solution required precise edge detailing that no territorial building guide addressed. Jakob cut strips of juniper bark from dead trees in the nearby foothills, selecting pieces 2 inches thick and 18 inches long. These bark strips had natural insulating properties and resisted rot better than other local materials. He placed them vertically between the packed earth floor edge and his log sills, creating a thermal break that prevented cold from conducting directly from the exterior walls into the floor mass. Installing this edge insulation required careful measurement and fitting. Jakob notched each bark strip to match the irregular contours of his hand-hewn logs, ensuring tight contact with no air gaps. He sealed the joints with pine resin mixed with hemp fiber, creating an airtight barrier that eliminated the drafts that had plagued his original wooden floor. This perimeter sealing proved crucial to the system's performance, as any air leakage would allow cold exterior air to circulate under the floor edge and reduce its thermal effectiveness. With the subgrade prepared and edge details complete, Jakob installed the final packed earth surface using techniques refined from his test section. He mixed local clay with coarse sand in a ratio of 1 part clay to 4 parts sand, adding just enough water to achieve proper compaction moisture. Working in thin lifts of 3 inches, he tamped each layer until it rang solid under his wooden tamper, building up to a final thickness of 2 inches above the limestone base. The completed floor system performed dramatically better than Jakob's original test had suggested. Temperature measurements taken during the winter of 1877 showed the packed earth surface maintaining 47 degrees at dawn, compared to 38 degrees for wooden floors in neighboring cabins. More significantly, the full-scale system achieved fuel savings that Jakob could measure in precise terms. His wood consumption dropped from the 5 cords he had burned during his first winter to 3 1/2 cords during the second winter, despite 1877 being notably colder than the previous year. These improvements came from the integrated performance of all system components working together. The drainage layers prevented frost heave and moisture problems. The full ground contact allowed heat exchange with the stable soil temperatures below. The edge insulation eliminated air infiltration that had compromised his earlier floor. Most importantly, the thermal mass principle that Green Rock had explained proved accurate. The dense earth absorbed heat during the day and radiated it back during cold nights, creating steady interior temperatures that wooden floors could never achieve. By spring of 1878, Jakob's floor envelope system had proven itself through a full heating season. But this success raised new questions about maximizing the thermal performance he had achieved. The warm floor provided a foundation for further improvements, particularly in how interior heat could be stored and distributed more effectively throughout his living space. Jakob's warm floor had solved the foundational thermal problem, but by autumn of 1878, he recognized a limitation that threatened to waste much of the heat his stove produced. The packed earth surface absorbed and held heat effectively, but his cabin's interior offered no additional mass to capture the radiant energy that his wood stove threw off during active burning periods. Like most frontier cabins, his walls were thin chinked logs with minimal thermal storage capacity, and his few pieces of furniture were lightweight pine boards that heated quickly but released their warmth within minutes of the fire dying down. The problem became apparent during his systematic temperature monitoring through the previous winter. While his floor maintained steady temperatures, the air temperature in his cabin swung wildly depending on stove operation. During active burning periods, interior air near the stove reached 75 degrees, but within 2 hours of banking the fire, temperatures dropped to 50 degrees or below. This temperature cycling meant he burned more wood maintaining comfort levels, and he frequently woke to cold air despite having a fire burning late into the evening. Most frontier settlers accepted these temperature swings as inevitable, but Jakob's European masonry background suggested a different approach. In the Bohemian provinces, he had worked on rural houses where large stone ovens and thick masonry walls stored heat from cooking fires and released it gradually through cold nights. The principle was simple but required substantial thermal mass, heavy materials that could absorb large amounts of heat energy and release it slowly over many hours. Applying this concept in Wyoming territory required adapting to local materials and conditions. Jakob could not build massive stone walls like those he had seen in Europe, but he could create strategic interior mass positioned to capture and store heat from his wood stove. The key was identifying the right materials, calculating appropriate sizes, and positioning thermal mass where it would receive maximum heat input during stove operation. His solution began with a stone bench that would serve multiple functions: seating, work surface, and heat storage. During the summer of 1878, Jacob hauled sandstone slabs from a natural outcrop 8 miles southeast of his claim. These local stones were dense enough to store significant heat, but soft enough to shape with his masonry tools. He selected slabs roughly 4 inches thick, cutting them to create pieces 2 feet wide and 4 feet long. The bench construction required precise positioning to maximize heat absorption from his stove. Jakob placed the stone structure along the cabin's south wall, 8 feet long and 18 inches high, with its face positioned 4 feet from where his stove would sit during the winter months. This distance ensured that the stone surface would receive intense radiant heat during active burning, but would not be so close as to create uncomfortable hotspots for anyone sitting on the bench. Building the stone bench directly onto his packed earth floor created a continuous thermal mass system that multiplied the heat storage capacity beyond what either component could achieve alone. The bench's 800 pounds of sandstone sat in direct contact with the floor's thermal mass, allowing heat to flow between the two systems and creating a combined storage capacity of over 4,000 pounds of dense material. This integration meant that heat absorbed by either the floor or the bench could migrate throughout the entire mass, evening out temperature differences and extending heat release periods. But maximizing the system's performance required additional modifications to capture solar energy during daylight hours. Jakob learned this technique during a second consultation with Chief Green Rock, who visited the cabin construction during late summer. The Shoshone elder examined Jacob's stone bench and nodded approvingly, but then pointed to the packed earth floor surface and made scraping motions with his finger. Green Rock explained through gestures and broken English that winter lodge floors were treated with dark materials to catch sun heat. He showed Jakob how his people mixed clay with charcoal dust to create dark slip coatings that absorbed more heat from fires and sunlight streaming through lodge openings. "Dark floor drink light make warm," he said, pressing his palm against the darker areas of soil where previous fires had burned. This insight led Jakob to modify his floor surface treatment. After applying the linseed oil seal he had used successfully the previous year, he prepared a thin coating of local clay mixed with finely ground charcoal from his forge. This dark slip, applied in a thin layer and burnished smooth, transformed the floor from its natural tan color to a deep brown that absorbed significantly more heat from both stove radiation and the limited winter sunlight entering through his south-facing window. The positioning of his wood stove became critical to the integrated thermal mass strategy. Instead of placing the stove in the center of the room for general heat distribution, Jakob positioned it so that its primary radiant surface faced both the stone bench and the largest area of packed earth floor. This arrangement meant that during active burning periods, radiant heat struck the thermal mass surfaces directly rather than heating only the lightweight cabin air. Testing this configuration during the winter of 1878 to 79 produced measurable improvements in heat retention. Jakob's temperature log showed that the stone bench surface reached 95 degrees after 2 hours of active stove operation. More importantly, the bench retained useful heat for extended periods. 6 hours after banking the fire, the stone surface still measured 68 degrees, warm enough to provide radiant comfort to anyone sitting nearby. The combined floor and bench system created heat storage that extended well beyond previous performance. While neighboring cabins experienced interior air temperature drops of 15 to 20 degrees within 3 hours of their fires dying down, Jakob's cabin maintained more stable conditions. His interior air dropped only 8 degrees during the same period, and the warm surfaces continued radiating heat that made the space comfortable even when air temperatures fell into the 40s. These thermal improvements translated directly into fuel savings that Jakob could measure precisely. His wood consumption for the 1878 to 79 heating season totaled 2 3/4 cords, a reduction of nearly 25% from his previous winter despite colder weather conditions. The stone bench system had captured and stored heat that would otherwise have been lost up the chimney or through the walls, extending the useful energy from each piece of firewood. More significantly, the thermal mass strategy created comfortable conditions that extended beyond mere temperature measurements. The warm bench provided a place to sit near radiant heat long after the fire had died down. The dark floor surface felt pleasant underfoot, even during early morning hours when air temperatures were coldest. The combined mass system eliminated the sharp temperature contrasts that made neighboring cabins uncomfortable despite adequate heating. By spring of 1879, Jakob had proven that interior thermal mass could multiply the benefits of his packed earth floor system. But this success also revealed new challenges around moisture control, air quality, and system maintenance that would require additional refinements to achieve optimal year-round performance. The success of Jakob's thermal mass system through the winter of 1879 revealed new vulnerabilities that threatened to undermine his achievements. The warm, stable interior environment that his floor and bench provided had created unintended consequences that became apparent during spring inspection. Field mice had established extensive burrow networks along the exterior foundation line, drawn by the consistent warmth radiating from the floor edges. More troubling, moisture problems had developed at specific locations despite his careful drainage preparation, creating damp spots that could compromise the floor's structural integrity. The rodent issue surprised Jakob because it differed markedly from problems experienced by his neighbors with wooden floors. Andrew Merrill's cabin, built with traditional raised flooring, suffered occasional mouse intrusions during harsh weather, but the pests typically moved through quickly and caused minimal damage. Jakob's earth floor system, however, had created an attractive permanent habitat. The warm perimeter where his packed earth met the log sills provided ideal conditions for mice to establish winter nests, and the dense floor prevented easy detection of their tunneling activities. Jakob discovered the extent of the problem during his annual foundation inspection in April of 1879. Examining the exterior base of his cabin, he found a network of mouse tunnels extending 18 inches out from the foundation line and burrowing under the floor edge. These tunnels compromised the thermal integrity of his perimeter ceiling and allowed cold air infiltration that reduced floor edge temperatures by several degrees. Worse, the mice had been bringing organic debris into their tunnel systems, creating pockets of decomposing material that could attract moisture and eventual rot. Solving the rodent infiltration required a defensive barrier system that would prevent burrowing while maintaining the thermal performance of his floor edge details. Jakob developed a solution using materials available on his claim and techniques adapted from his European experience with grain storage buildings. He excavated a trench 12 inches wide and 8 inches deep around the entire perimeter of his cabin, extending from the foundation line outward. The key innovation was a buried metal barrier that mice could not penetrate or circumvent. Jakob acquired thin galvanized sheet metal from the Territorial Supply Depot, cutting it into strips 6 inches high and 18 inches long. He installed these strips vertically in his perimeter trench, with the top edge positioned flush with his interior floor level and the bottom edge extending 8 inches below grade. Most importantly, he bent each strip outward at a 90-degree angle before backfilling, creating an underground flange that prevented mice from digging under the barrier. This rodent-proofing system required precise integration with his existing floor structure to avoid compromising thermal performance. Jakob positioned the metal strips so they made direct contact with his juniper bark edge insulation, ensuring no thermal bridge between the interior floor mass and the exterior ground. He sealed the joints between metal and bark using pine resin mixed with fine sand, creating an airtight seal that maintained the thermal integrity while blocking animal access. But the rodent barriers revealed a secondary moisture problem that his original drainage system had not anticipated. During the wet spring of 1880, Jakob noticed dampness developing at the northeast corner of his floor, where snowmelt and spring runoff pooled against his foundation line. The problem occurred because his metal barrier, while effective against rodents, also blocked lateral moisture movement that his sand and limestone drainage layers were designed to handle. The solution required modifying his drainage system to work with the rodent barriers rather than against them. Jakob learned this technique during a visit from a Northern Plains native builder who had been traveling through the territory with a trading party. The builder, experienced in constructing earth lodges in regions with both severe winters and heavy spring runoff, examined Jakob's moisture problem and suggested a 2-layer approach to groundwater management. The visiting builder demonstrated how successful earth floors required both vertical drainage to handle surface water and lateral drainage to manage subsurface flow. Jakob's original sand and limestone layers handled vertical drainage effectively, but the addition of the metal rodent barriers had interrupted the lateral flow patterns that carried groundwater away from the foundation area. The solution was adding a shallow drainage channel just inside the metal barrier, filled with coarse gravel that could carry water around the foundation perimeter. Installing this interior drainage required careful excavation along the inside edge of his floor, creating a narrow channel 3 inches wide and 4 inches deep. Jakob filled this channel with creek gravel, ensuring that water entering the channel could flow around the entire cabin perimeter and exit at a low point on the downhill side. This interior drainage worked in conjunction with his existing sand and limestone layers, creating a complete moisture management system that prevented water from reaching the floor surface while maintaining the rodent-proofing effectiveness. The moisture control improvements led Jakob to recognize a broader ventilation challenge that affected both air quality and humidity levels during different seasons. His tightly sealed cabin, optimized for winter heat retention, trapped interior moisture during warmer months when cooking and washing generated water vapor. The stone bench, which provided excellent heat storage, also absorbed moisture during humid periods and released it during dry spells, creating humidity fluctuations that could affect both comfort and material preservation. Managing seasonal ventilation required a controllable system that could provide summer air exchange while maintaining winter thermal performance. Jakob developed a solution using small vent openings positioned strategically around his cabin perimeter. He cut circular openings 6 inches in diameter through his log walls near floor level, spacing them 8 feet apart around the cabin perimeter. During winter months, he sealed these vents with fitted wooden plugs wrapped in wool felt, maintaining the tight envelope necessary for thermal efficiency. During summer months, Jakob removed the plugs and installed simple wooden louvers that allowed controlled airflow while keeping rain and insects out. This seasonal ventilation system provided cross-flow air movement that dried out any accumulated moisture in his floor system and stone bench, while preventing the overheating that could make the thermal mass uncomfortable during hot weather. The controllable nature of the system meant Jakob could adjust ventilation levels based on weather, conditions, and seasonal requirements. The integration of rodent barriers, improved moisture control, and seasonal ventilation created a complete environmental management system that protected Jakob's thermal innovations while maintaining their performance advantages. By autumn of 1880, his refined system had proven effective through a full annual cycle. The rodent barriers had eliminated mouse infiltration completely, while the enhanced drainage prevented any recurrence of moisture problems. The seasonal ventilation system maintained comfortable humidity levels year-round without compromising winter heating efficiency. These refinements represented the completion of Jacob's floor system development, creating a comprehensive approach that addressed not only thermal performance, but also durability, maintenance, and seasonal adaptation. The system was now ready for the ultimate test that would prove its superiority over conventional frontier building methods. The winter of 1887 brought weather conditions to southeastern Wyoming territory that tested every homestead building technique settlers had developed over the previous decade. By November, sustained temperatures dropped below 0 degrees for weeks at a time, with recorded lows reaching 30 below zero at the Territorial Weather Station in Cheyenne. More challenging than the cold itself was the relentless wind that drove across the plains at sustained speeds of 20 to 30 miles per hour, creating wind chill conditions that made exposed travel deadly and pushed every cabin's heating system to its absolute limits. Jacob's refined floor system faced its most severe trial during the February blizzard of 1888, a storm that lasted 6 consecutive days and deposited 4 feet of snow while maintaining temperatures below 20 below zero throughout the duration. The storm isolated homesteads completely, making wood gathering impossible and forcing settlers to rely entirely on whatever fuel they had stockpiled. For many cabins built with conventional methods, the extreme conditions revealed fundamental weaknesses that threatened occupant survival. Andrew Merrill's cabin, representing the standard territorial building approach, demonstrated the limitations of raised wooden floors under extreme stress. During the worst night of the February storm, with outside temperatures at 28 below zero and winds gusting to 40 miles per hour, Merrill recorded interior floor temperatures of 29 degrees at dawn despite keeping his stove burning continuously through the night. The wooden planks transmitted cold so efficiently that ice crystals formed on the floor surface near the exterior walls, and Merrill was forced to wear boots inside his cabin to avoid frostbite. The fuel consumption required to maintain minimal interior temperatures in Merrill's cabin reached crisis levels during the extended storm. His stove burned a full cord of wood during the 6-day blizzard period, exhausting nearly a quarter of his winter supply in less than a week. Even with this intensive fuel consumption, his cabin interior never exceeded 45 degrees during daylight hours, and occupying the space required constant proximity to the stove, along with heavy winter clothing worn continuously indoors. Jacob's integrated thermal system performed dramatically differently under the same extreme conditions. His packed earth floor maintained surface temperatures of 48 degrees even during the coldest night of the storm, while his stone bench retained enough heat to provide comfortable radiant warming 6 hours after banking his evening fire. Most significantly, his interior air temperatures never dropped below 52 degrees, creating conditions where normal indoor clothing remained adequate throughout the crisis period. The fuel efficiency advantages of Jacob's system became most apparent during the extended nature of the February storm. While Merrill burned a full cord during the 6-day period, Jacob's total wood consumption was 3/4 of a cord, achieving superior interior conditions while using 25% less fuel. This efficiency margin represented the difference between surviving the storm comfortably and facing potential fuel exhaustion with weeks of winter remaining. But the most revealing test of system performance came during the recovery period following the storm, when damaged cabins revealed structural failures caused by extreme thermal stress. Hans Mueller's cabin, built with conventional raised flooring, suffered significant damage when frost penetration beneath his floorboards caused ground heaving that cracked 2 floor joists and warped several planks beyond repair. The repair cost totaled $18 in replacement lumber plus a week of construction work during harsh weather conditions. Jacob's earth floor system showed no structural damage despite the extreme conditions, demonstrating a resilience that surprised even him. The integrated drainage and moisture control systems prevented frost penetration, while the thermal mass maintained ground temperatures above freezing even during the worst cold. When spring inspection revealed the full extent of winter damage across the territory, Jacob's cabin required no structural repairs related to foundation or floor systems. The performance contrast during the killing winter marked a turning point in local acceptance of Jacob's building methods. Nathaniel Wright, the district land office inspector who had previously questioned the packed earth approach, visited multiple homesteads during spring damage assessments. His official report to the territorial office noted that the German settlers' earth floor construction showed superior performance during severe weather conditions and merits consideration for standard building recommendations. Wright's endorsement carried weight because it was based on measurable performance data rather than theoretical arguments. His inspection records documented fuel consumption, structural damage costs, and habitability ratings for cabins across his district. The data showed clearly that Jakob's thermal system achieved better interior conditions while using less fuel and requiring fewer repairs than any conventional cabin in the area. Word of the performance advantages began spreading through informal networks that connected homesteaders across the territory. During the spring barn-raising season of 1888, several settlers approached Jakob privately to ask about his floor construction methods. Unlike the earlier mockery, these conversations focused on practical details, excavation techniques, material ratios, and installation procedures that could be applied to new construction. Jakob's most significant convert was a young homesteader named Thomas Brennan, who had filed a claim 12 miles west of Jakob's property. Brennan had witnessed his neighbor's cabin become uninhabitable during the February storm and was determined to build more effective shelter before the next winter. He worked alongside Jakob for 2 weeks during summer of 1888, learning the complete floor system construction process from subgrade preparation through final sealing. Brennan's cabin, completed in autumn of 1888, incorporated all elements of Jakob's refined system: packed earth floor with drainage layers, thermal mass stone bench, rodent barriers, and seasonal ventilation. His first winter performance matched Jakob's results closely, achieving interior temperatures consistently 8 to 10 degrees warmer than neighboring wooden floor cabins, while using 30% less firewood. The success of Brennan's cabin provided proof that Jakob's techniques could be transferred successfully to other builders and sites. This transferability was crucial for broader adoption, as it demonstrated that the system's advantages resulted from sound building principles rather than unique site conditions or exceptional craftsmanship. By 1889, 3 additional homesteaders in the district had installed packed earth floors using variations of Jakob's methods. The legacy of Jakob's thermal floor system extended far beyond its immediate applications in Wyoming territory. During the early 20th century, agricultural extension services began documenting traditional building techniques that had proven successful on the frontier. Jakob's integration of thermal mass, moisture control, and efficient heating became recognized as an early example of what would later be called passive solar design principles. Modern building science has validated the core principles that Jakob discovered through practical experimentation. Contemporary research on thermal mass, ground coupling, and building envelope performance confirms that dense earthen floors can outperform lightweight materials in appropriate climate conditions. The concept of integrating thermal storage with heating systems has become standard practice in energy-efficient construction, though few modern builders realize that frontier homesteaders developed these techniques over a century ago. Jakob Klaus had proven that questioning conventional wisdom and applying traditional knowledge could produce superior results even in challenging frontier conditions. His packed earth floor system demonstrated that innovation often meant looking backward to older practices rather than forward to newer technologies.